same thing with parts.
Ah.
And that went over my head. I was like, what?
That's good. That's good. Yeah. Oh man, I think that most of my jokes are dad jokes, but that's okay. I've come to terms with that. So, lecture 3.7, the final lecture in chapter 3 of the dynamic systems notes. Bridge between state space and input-output differential equations, and, oh yeah, transfer functions along the way, which transfer functions we'll talk about a lot later, but for now we're just going to wave at them as we pass, okay? The Laplace transform, L, is cool AF. Okay, so you guys remember the Laplace transform. It is used to solve differential equations and define the transfer function H. You know, just another awesome dynamic system representation. So we've been representing systems as, we started out with input-output ordinary differential equations, right? They looked like the equations you solved in your differential equations class. We now have state space models, which look a little bit different, the vector sort of system of first order differential equations. And now we're talking about the transfer function H. So for now, we'll use it as a bridge, the transfer function, we'll use it as a bridge between state space and input-output differential equation representations, merely waving at transfer functions as we pass through. I made that joke last year when I wrote this too, turns out, the waving part. Later, transfer functions will be considered extensively. So we're just going to talk about it for a brief moment today. So a quick introduction to transfer functions. Let a system have an input u and output y. Let the Laplace transform of each be denoted u and y. So I don't know if you guys used that convention in your differential equations class when you were introduced to Laplace transforms, but we would say that the Laplace transform of u of t we will often write as capital U of s. So, and same with Laplace transform of y of t. We'll often write as capital Y of s. Great. A transfer function, h, is defined as the ratio of the Laplace transform of the output over the input. So y over u. That's the whole definition. It's really not that bad, the definition. There's a lot of stuff you can do with it, and we'll talk about it later. But we're just going to use it for just a little bit here today. The transfer function is exceedingly useful in many types of analysis. One of its most powerful aspects is that it gives us access to thinking about systems as operating on an input and yielding an output. Okay, so we have, it's very, very closely associated with the block diagram. So you think of U going in to the block. We'll talk more about block diagrams later, but U going in, the transfer function operating on the input and yielding an output. Okay, so that's a very common representation we'll use for a system. Input, output, and then the system itself, thinking of it as being a transfer function that transfers the input to the output. So bridging transfer functions and I/O differential equations. Consider a dynamic system described by the input-output differential equation with variable y representing the output, dependent variable time t, variable u representing the input, constant coefficients a, b, order n, and m less than or equal to n. So this is just like all making sure that we've got all of these things correctly defined. We have this representation. So this is our I/O differential equation form. that we worked with quite a bit early on. So a first order one we would say was tau dy dt plus 1 equals some constant, call it b, times the input u. So that would be a first order one. But then you can go to second order, third order, fourth order, etc. So we're going to use this general form. We're going to derive transfer function, the transfer function definition from this equation. So the Laplace transform L of, this is not correct equation number. It's equation 3.5. Of equation 3.5 yields something interesting. So we're going to take the Laplace transform of both sides of this equation. Okay? Assuming 0 initial conditions, we take the Laplace transform of the left-hand side. And I have this weird spacing so that everything lines up. So Laplace transform of the left-hand side has to equal the Laplace transform of the right-hand side, right? So that implies that, so the Laplace transform, you may recall, can be distributed across the sum that's inside the parentheses. So Laplace transform of the nth time derivative of y plus some constant. The constant can come out front. Remember, the Laplace transform has an integral definition, right? So the Laplace transform, if you have the Laplace transform of some constant times a function, the constant can be pulled out, just like you can pull out the constant in an integral, right? And we've got the left-hand side having all these Laplace transforms of time derivatives of y, and the right-hand side having the Laplace transforms of all these time derivatives of u. So there's you may or may not remember this nice Laplace transform identity, but the Laplace transform of, we'll say, dy dt is equal to, do you guys remember? S times the Laplace transform of y, which we could just write S and then capital Y, right? So, and then if you keep doing that and one more, so higher ordered time derivatives, you're just going to end up with more S powers, right? S squared, S cubed, etc. So that's what we're recognizing here is we have all these Laplace transforms of time derivatives. So the nth time derivative of y, when we take the Laplace transform of it, it becomes S to the n y. When you take the n minus first derivative of y, we get S to the n minus 1 times y. So instead of derivatives, you just get powers of S that correspond to the order of the derivative. So now we've got all these powers of S on the left-hand side with the original coefficients as well. And then every single term has y in it, right? Similarly, on this side of the equation, the right-hand side, we have powers of S all the way up to m, the highest time derivative of u. So all the way down to the lowest. Okay. So now this equation is no longer a differential equation in the Laplace domain, right? It's an algebraic equation, which is probably the number one powerful aspect of Laplace transforms, is it takes things from the differential equation solving realm into the algebraic solving realm, which is really nice. So we can solve for y. And notice that this entire left-hand side, you can factor y out. And this entire right-hand side, you can factor u out. So y equals, it's going to be a big fraction times u, the input. I'm going to just go very big just to make sure. The left-hand side that's got y on it is going to become the denominator, right? Because we have to divide that over. So we're going to have s to the n plus a n minus 1, s to the n minus 1, plus, and then a lot of terms, down to a1 s to the 1, right, or just s, plus a 0, s to the 0, or just 1, right, times u. And then in the numerator, we have whatever was on the u side, but we factored u out, right? So we just take whatever's left after we factor u out. So bm s to the m plus bm minus 1 s to the m minus 1 plus all the way down to b1 s plus b0. Cool. So if we were to take the inverse Laplace transform of y, we would find the forced response. Okay? Yeah, question.
Is there supposed to be a in front of the s to the n?
You can do it that way. So if you look back to the original equation, I assumed that we could make this coefficient 1.
Oh, okay.
We could do an and use that all the way through, but you can always make one of your coefficients 1 if you divide both sides of the equation by whatever that coefficient is. So I just assume we're always going to do that for the first term. It is a convention that some people use. I'm not super worried about it either way, but just make sure you're consistent.
I'm just making sure that it didn't just disappear.
It's good to check. Yeah, it's good to check. Symmetry is something that we can use to check ourselves, right? We like that. So if we take the inverse Laplace transform of this expression for y, we would get y of t, and that would be the forced response, which is what is, because we assume the initial conditions were 0, right? Back up here. Remember when we take the Laplace transform, this Laplace transform, if you were not considering the initial conditions to be 0, then we would have this term, I believe it is just y of 0, the initial condition for y. And since we assumed all those were 0, I didn't write that, but I probably should have. So remember, when we take those Laplace transforms of the time derivatives, all these initial condition terms show up. We ignored them. So when we end up solving for y at the end, if we were to take the inverse Laplace transform, it would just be the forced response because we already assumed the initial conditions were 0. Okay, however, this is not our primary concern. So this is what you guys did in differential equations, though. That was the way that you solved your differential equation, is you took the inverse Laplace transform at that point. But rather, we are interested to solve for the transfer function h as the ratio of the output transform y to the input transform u. So we have h being defined as y over u, and we've got this expression. So all we did is divide both sides by u. So u, and then these cancel. So y over u is equal to this expression. But remember, that's the definition of the transfer function, is the ratio of y over u. So exactly the reverse procedure then can be used to convert a given transfer function to an input-output differential equation. So we just went from, so I'll say, we just went from ODE, the differential equation, to transfer function, right? So h of s. And that was this procedure that we just saw. We can also go the other way, right? We can go from a transfer function to an ODE by just reversing this procedure. Now, you might think, gosh, there was kind of a lot. I mean, we took Laplace transforms, and like, there were a lot of terms. But fortunately, there are a couple things that make this actually quite simple. The first is that most of the time you don't have n and m. You've got like a third order system where n is 3. So you don't have like a million terms. But also, you don't have to go through the whole derivation every time. It's fine to if you want. But notice the really easy way we could go from the original expression, which was 3/5, this guy, and we see that where the ANs and the BMs are, right? And we see the time derivative orders, okay? And then we come down to the transfer function, and we just see, oh, the BMs show up there, right? And the ANs show up there. So the BMs show up in the numerator, the ANs show up in the denominator. The powers of S are just n and m reducing down to 0. So that's just the same order as the time derivatives on the terms, right? So you can just skip down to this. When you see a differential equation, you can just immediately write down the transfer function. If you have a transfer function, you can then go backwards and say, oh, well, this must have come from the nth time derivative of y. This must have come from the n minus first time derivative of y. This term must have come from the first time derivative of y, etc. So this is how to go back and forth. Okay. So now that's great, but what I just did there was I gave you guys a bridge to transfer functions. But we aren't really focusing on transfer functions right now. We are focusing on state space models. So why did I bring back ODEs from the beginning and then talk about transfer functions? It seems like a bridge to nowhere, as they call them, right? So this is our bridge. We need to now bridge between the transfer function and state space models, okay? So we'll build that bridge now. So this part of the bridge is ODE, or not ODE. This one is transfer functions and state space models. I'll just write SS for state space. And we're going to learn how to go from state space models to transfer functions. That's the only direction. This is a one-lane road for us in this course. There are ways to do this, to go from transfer functions to state space models, but it's not unique, and there are a lot of caveats, and we're not going to get into the details of that. So right now we're going to just focus on this guy, how to go from a state space model to a transfer function. So given a system in the standard form of a state equation, so dx dt equals ax plus bu, we take the Laplace transform to yield, assuming 0 initial conditions. So you take the Laplace transform of the left-hand side. So the left-hand side has a time derivative, right? So a time derivative, assuming 0 initial conditions, is going to be s x. So now it's still a vector x, but I put capital because it's the Laplace transform of x now, right? So one time derivative gives us the s. The Laplace transform of x gives us capital X equals a times the Laplace transform of x again, so capital X, plus b times the Laplace transform of u, or capital U. And note that A and B are constant matrices. Okay, if we're working with linear time invariant systems, which is the focus of this course. So the Laplace transform allows us to pull the constants out front, right? Okay. So we can solve this equation for the state. So if we want to know the state, there's a state shows up on both sides of the equation. So we can say x. So we subtract that one over. We factor out the x. And then we have to left multiply by S times the identity matrix minus A inverse B U. So S times the identity matrix is there so that we have proper dimensioning. So if the A matrix is 2 by 2, then I is a 2 by 2 identity matrix. Remember, the identity matrix is the matrix of 1s along the diagonal and 0s everywhere else. So if A is 2 by 2, then S times I is going to just be S, 0, 0, right? 2 by 2 identity matrix multiplied by S. The S goes and multiplies each term in the matrix because it's a scalar multiple of a matrix. So if you're feeling like, oh man, matrices, it's been a little while since I thought about them, might be worth going through and reviewing those a little bit. We're not getting into huge detail, but you do need to be able to take the inverse of a matrix. You need to be able to multiply matrices. You need to be able to subtract matrices for this portion. Okay. So the standard form of the output equation yields the output solution. So, I mean, before we move on, I guess we should mention, we just solved for x. We just solved for the state. So we actually solved our state equation in the Laplace domain. We don't have the solution in the time domain, so we'd have to take the inverse Laplace transform of the right-hand side to do that, which is possible. It's just not always easy to do. Okay, so the standard form of the output equation yields the output solution, y equals HU. And let's see. This is not, I don't know. I don't. I mean, it's true. We skipped a step. I mean, we didn't really skip it. I just folded it into this form here. So the standard form of the output equation. Let's remember what that is. I didn't write it down, but I feel like we need to. So y equals, well, in the time domain, it's y equals cx plus du, right? In the Laplace domain, if we were to take the Laplace transform of both sides, we would have capital Y equals c capital X plus d capital U. So if we were to plug in x, our solution for x, into the output equation, then you would come up with an expression for what y is in terms of something times u, right? So there's a u that would come from this x term, and there's a u that would come from this term. So I'll actually do the steps here. I don't know why I didn't write them out, because I think it's not that hard to show. So Si minus A inverse. There was a C, right? And remember, the order of multiplication matters with matrices, right? So there was a C times X, which is now Si minus A inverse B U plus D U. We can factor out U on the right-hand side, so C, so I'll do this, C Si minus A inverse B plus D, and then the factored out U. So that is the solution, and we're going to call this H. So I'll write H. H of S equals C times Si minus A inverse B plus D. Right, so this expression. And why did we call this? We define the matrix transfer function to be H. So it's definitely a matrix. It's not exactly like the previous definition of the transfer function, because the previous definition wasn't a matrix definition. It was just scalar. So why do we feel justified calling this the transfer function, do you think?
Because there's a difference between the input and the output.
Right, exactly. It relates the input U to the output Y. So this is in this form, right? So Y equals HU. Y equals HU. It operates on the input U, and it gives us the output Y, which was our definition in the scalar case of the transfer function. So when you have a matrix case, it's just a matrix instead of a single scalar function. So so the element Hij is a transfer function from the jth input, Uj, to the ith output, Yi. So we have a bunch of transfer functions packed into this matrix transfer function. So each input gets a transfer function to each output. Okay? The reverse procedure of deriving a state space model from a transfer function is what is called a state space realization. So that was this dashed line right here. This is called a realization. And just a couple notes on that. It's not a unique operation. So there are different realizations for a single transfer function. Choosing which variables will be your state variables determines what the realization will be. And remember, state variables, the number of state variables is unique, but which variables they are is not unique. We have a procedure that does determine what they're going to be. We have a procedure that determines them, but that's just for the one construction form that we have, and not a realization in this sense. So, and the other thing to note about this is we're not going to consider that here. So we're not going to. There is a description in the Rowell and Wormley text of how to go from transfer functions or input-output differential equations to state space models, but that's not something that we're going to consider. So what have we done in this lecture then? We've got ODEs, and we've got transfer functions, and we've got state space models, right? So the first section here, we learn how to go from ODEs to transfer functions. And we also talked about how it's very easy to go back, which is to say you just recognize which coefficients and powers of S are associated with time derivatives the input and the output. So we learned how to do that first. And then we just learned how to go from a state space model to a transfer function model. So the process that we're going to use, so for now, we're not interested in the transfer function as an end game. This is something that we will be interested in later. But for now, we're not interested in it as an end game. We're just using it as a bridge. So we're going to go from state space to transfer functions, and then from transfer functions to ODEs. The reason being is that for now, that's the only way we know how to solve the state equation, right? The state equation, we haven't learned how to solve it directly yet. So we're stuck having to turn it into a regular ODE for now. And then we can solve it. So for now, we'll follow this path. We'll go along this, and then we'll go along that and get an ODE. So this brings up this system representation summary or map that I've drawn. So this is something that's in the appendix of the text. So C1. And this shows all the different system representations that we use in this class. So it's a little bit hard to see if I go all the way out, but I just want to see like a bird's eye view first. Oh, my face is frozen. Fun. The schematic is usually the first thing we do, right? So there's like the real system, and then we draw a schematic for it. So that's one representation. And then we can do a couple other graphical representations. So the linear graph, we spent a lot of time discussing. So the linear graph representation we're familiar with. Block diagrams, we haven't talked about very much, but we'll continue talking about them more in the future. Another graphical representation. Then state space models, we definitely have been discussing how to construct. I/O differential equations are representations we started with. This is what we started at the very beginning of the class with, representing dynamic systems as differential equations, scalar ones. And then we just learned about the transfer function along the way here. So what we did today was learn how to go from state space using this nice equation for H to a transfer function. And then from a transfer function to a differential equation, remembering that S and S is just a time derivative. So if you go from a transfer function to an ODE, that's the route that we learned today. So we just learned this to that today. But this is a map of all of the representations that we'll be doing in system dynamics as well. So this is for this semester and next semester. So we already are hitting, like, we've got this one, we've got this one, we've got this one, and this one. So there aren't a whole lot more. There's really just, there's the frequency response function, which we'll get to next semester. And then there's the block diagram, which we'll also be talking about next semester. So pretty fun stuff. So it's like we keep learning all these new system representations, but I don't want you to feel like there's an infinite number more. We're pretty much getting to the end of new system representations. So this kind of helps you map it out. The next thing I wanted to show is that I forgot that I had made this really beautiful summary of one-port elements. So this is really good reference for summarizing the chapter, well, the stuff that we have learned in this chapter and the preceding chapter. So it shows you, in each domain, the across and through variable. So if you wanted to know what the through variable was for an electrical system, you would see it shows up there, currents I. The A-type energy storage elements are here, right? And I give you the name of it. I give you the symbol we use. I give you the elemental equation for it, and I give you the impedance. I included in here fluid and thermal elements, which we won't talk about until next semester. But so for now, we just need these ones over here. And T-type energy storage elements and what their elemental equations are, and then D-type as well. So, and then this last row, impedance, we're not talking about that in this portion of the course, but we'll get to that later. So this is sort of like the one table to rule them all, I call it. So like this is a good reference. So I would bring this to the test, for instance. Yeah.
Rico, just
Yeah.
a question. What's FR in food and thermal? Up there. What's FR?
Oh, here?
Yeah.
It's a volumetric flow rate. Probably needed another dot there. Yeah. Yeah.
I was thinking to frequency, it doesn't make sense.
Yeah. I think it's yeah. I think I should have put another period in there. Volumetric flow rate. Okay. Any questions on any of that? So hopefully your homework's going well. And let me know if you have questions.